Okay, let's get started. Hello. Hello. Hi. Welcome to class. I'm glad that you all are in a much better mood than you were on Friday. I've never seen such a collection of ashen faces than I saw as you guys turned in those exams. Man, it felt like I had just taken away your firstborn or something. It was just bad. I have not started grading the exams yet. This is the downside of having two classes, both with exams due on the same day. Didn't really get a whole lot done on the other exams either, but those ones are going to be easier to grade than... Well, I don't know. It's easy to grade blank problems, and so, I mean... So trying to... sorting out what people did on this make the file handling work business is going to be an adventure. So... Or didn't do. Please remember that we have a lab that's due. It sounds like I'm a broken record, but this one's probably the most involved of all the labs except for the last one. So, so difficulty level, I told you lab 1's one of the toughest ones. I don't think this lab is as confusing to understand what you're supposed to do as lab 1, but there's a whole lot more to do on this lab. There's a whole lot of steps involved. So I hope that you've made some headway. Anyone? Anyone? No one? So, I would highly recommend, okay, this lab you are tied to the lab room. There's not a whole lot you can do outside it. You need the lab equipment, okay? I would highly recommend spending some good quality time with Rohit tomorrow, and he will be very helpful. But anyway, so he's there from, 10:30 to 4. So, and if you're logging in on distance, make sure you access his WIMBA session to ask questions or call me on the phone or whatever. But there's a lot to do with this lab, and it's a lot of work. So. And it can, when I say it's not as confusing to understand what you're supposed to do as lab 1. Lab 1 was one algorithm you had to wrap your fingers around. It was kind of confusing on that one algorithm. There's a whole lot of steps that I've gone through in the lab write-up for lab 4, and it's easy to lose track of what in the world am I doing, and it's easy to get lost in all the steps of where am I going. So please do come and talk to me if your head's spinning. I would really love to help. Okay? Questions? Aside from, how did I do on the test? Mitch?
On the code for lab 4, there's 2 macros that we have filed in, but you do the whole do while 0 business, and I guess I didn't quite understand why.
Okay, so in the files that I've given out for lab 4, there are a couple of macros defined, and the macros utilize a do while 0 construct. They surround the code that they do inside a do while block. Okay, now the reason why you put the contents of a macro inside, or in certain circumstances, you put the contents of a macro inside a do while block is if you want that macro to look like a function call. If you have a do while block, it has to end with a semicolon, and the compiler will yell at you if it doesn't. So this is a way of syntactically enforcing that you put a semicolon at the end of your macro invocation. Otherwise, you don't have to put a semicolon there, and all of a sudden your compiler isn't going to force the user of your macro to have your macro code look like a function call. The do while 0, it will execute one iteration of the do while loop, and it will terminate as soon as it gets to the while 0. So it will happen exactly once. The compiler will also see that this is a loop that only loops once, and it's guaranteed to only loop once, so it will compile out all the jumps. So the other deal is that it defines a block and allows you to declare local variables inside the macro if you need to. So it provides a block and a scope for local variables. So back in the lecture that I lectured on macros, you remember this? I talked about the do while stuff. So
Yeah, but I guess I don't see how it's necessary.
it is not necessary. It is never necessary to put the do while block. It's just good practice.
Even if you want it to look like a function call.
If you want it to look like a function call, there are times where you don't want to do this inside a macro. You'll see plenty of examples of that when I give you homework assignment for Chapter 6. This is Chapter 6 stuff, by the way. Hope you've read Chapter 5, 4, 3, 2, and 1. Okay. I'm getting blank stares again. Wait, read the book? What's he talking about? Okay, so, if you remember last time we talked about Chapter 5, sorry. In Chapter 5 we were talking about fault tolerance and how to do fault mitigation, how to make sure that you can develop systems and software that are resilient to the occurrence of faults. At the end of that lecture, we talked a little bit about exception handling. And Chapter 6 is all about exceptions and exception handling. Chapter 5 is more conceptual in nature. There's not a whole lot to wrap your fingers around and say, this is code that I'm going to put in my embedded system. It's more concept, more theory, more conceptual. Exception handling starts to bridge the gap between concept and theory and something that I can actually sink my teeth into and apply in an embedded system. Unfortunately, I'm teaching you the language C, and C is the wrong language for everything except for if you're actually going to do something practical in industry. So C has no real support for exception handling. So we're going to make C look like Ada, because Ada does a great job of doing exception handling. And you're going to use a C preprocessor to make C code look like Ada code. Great. So that's the point of this lecture, is to talk about exceptions, exception handling, and I'll talk about what are these macros that you're going to be defining at the end. Okay. So we're going to start more on the theory end, talking about exceptions, exception handling, why we need exceptions, and what are the different approaches and different ways that different programming languages use for doing exception handling. And then we'll dig into what Ada does, a little bit about what Java does. I'll try not to gag. And then a little bit about what C does for exception handling. Okay. So, synchronous exceptions. The book classifies exceptions and exception handling into different categories. It talks about synchronous exception handling, or synchronous exceptions and asynchronous exceptions. Okay. A synchronous exception is one that your program explicitly raises, or something that your program does explicitly causes an exception to be raised. Okay. An asynchronous exception is something like an interrupt, where your program is it's minding its own P's and Q's, and all of a sudden something happens. It didn't run a faulty instruction, or it didn't access a memory location that it shouldn't have accessed, or it didn't trip over an error that caused an exception to be raised. It didn't call a function which raises an exception. The program didn't do it. So this is asynchronous exceptions are like your 3-year-old. It's not my fault. I didn't do it. It's my brother's fault. Oh, come on. Oh, gosh. All right. Gonna have to resort to Princess Bride quotes to try to keep you guys awake. Okay. Anybody watch the movie, by the way, during the course of the exam?
I'll be honest. I watched everything with that little guy that I was so...
What? You didn't fall? Inconceivable. You're using that word. Okay, so Ada has different types of exceptions that can be raised. So these are exceptions that the runtime system. This is what the RTS in this bullet means. RTS is not real-time systems in that one. It means the Ada runtime system. Okay, the Ada runtime system defines a few different classes of exceptions: constraint error, program error, storage error, tasking error. Constraint error is when you have a variable that gets assigned a value that it can't be assigned. You not only say, so this would be like if you have an integer variable and you assign a floating point number to it. Or alternatively, with Ada, you can declare a variable and say that this variable can have a value that ranges between 0 and 100. And if you assign it the value 2000, you'll get a constraint error. Okay? The runtime system will raise that exception. Okay, so different exceptions can be raised. Exceptions can be handled. What is an exception handler? An exception handler is a block of code that deals with a problem that got raised. So you raise an exception, and you can have like a little subroutine or a function that gets invoked when that exception occurs. You kind of think about this in some sense like an interrupt and an interrupt handler. Okay? So we define a set of interrupts, and when an interrupt occurs, we want this particular block of code to get invoked. We want to stop what we're doing and go and do this, handle the interrupt, and maybe we'll come back and finish what we're doing later on. So an exception handler is this block of code that you want to run whenever a particular exception occurs. So a handler can be specific to a particular exception or a particular type of exceptions, or you can associate a set of exceptions with a particular handler. But the point is you have a handler is associated with exceptions. The domain of an exception handler refers to, I've defined this handler, and it's going to handle a particular exception or class of exceptions. When do the exceptions that get raised get routed to this handler? So if you have an exception handler with a program level domain, that means anytime, anywhere in your program, an exception of this type gets raised, it'll route the exception to be handled by this particular handler. We normally define exceptions in a finer granularity than that, so where we say, okay, within this subroutine, I might be calling other subroutines or other functions or doing some other things, but at the end of this, I'm going to define a block of exception handlers, and therefore, I've defined a block of code, and at the end of the block, I define a set of exception handlers. The handlers, the domain of those handlers refers to any exception that gets raised in the above block get routed to that exception handler. So the domain of the exception handler is when an exception gets raised, it gets routed to a particular handler. Over what scope of the program does that handler get applied to the exception that gets raised? Okay, to make that a little bit more concrete, a little bit less what in the world is he talking about, let's see an example here. Okay, block structured language like Ada. Okay, Ada is a block structured language, like C is a block structured language, like Java is a block structured language. Okay, we define blocks. The block in Ada, you have a declaration section and a set of executable statements, and then down here you have a set of exceptions. Okay, these are the subfields of the block, but the block is between the declare and the end. Okay, so inside the declare and begin, you can declare types, you can declare variables. So over here you're saying that temperature, this is kind of like a fancy type def in Ada. This is not declaring a variable, this is just declaring a type. So temperature is a data type. It's an integer, but an integer limited to the range 0 to 100. So now I can declare variables of type temperature, and all those variables will be restricted to the range 0 to 100. Okay? So suppose inside the begin block over here, after the begin, we've got a bunch of statements to read a temperature sensor, calculate the value, we assign it to a temperature variable, and then over here below exception, we list what the handlers are. So the domain of these exception handlers corresponds to the above block from the begin to the exception. Any exception that gets raised when control starts the statements in the begin block, those exceptions will get routed first down here to the exception handlers after that exception statement. Okay. C++ and Java, syntactically, they look identical. So you have a try block. So inside the try block, this is kind of like what we call a guarded section, where inside the try block we have executable statements. Those could lead to the raising of an exception. We have a catch block, and you can have multiple catch statements after the end of a try block. So inside the catch statement is a parameter that says this is the type of exception that I'm catching. So over here you have a set of statements. Inside the catch block you say exception type E. You have the handler for exception E in the catch block. Okay. The domain of this particular handler, where we're catching exception type E, the domain of that handler is the try block, the corresponding try block. If an exception of type exception type gets raised someplace else after we're done or before we enter this try block, this exception handler does not get invoked for that. Only once control flow enters here and before it leaves there do we end up getting an exception that, if we end up getting an exception of this type, will it end up getting routed to that handler? Okay? Okay, so the granularity of the exception handler domain. So let's think a little bit about whether or not it's acceptable to say that the granularity of a domain of an exception handler, if we associate that granularity with its corresponding block, is that a sufficient case for handling exceptions? Is that a good idea? So if we consider ADA code like what we've got here, suppose we've got subtype temperature, subtype pressure, subtype flow, and then we've got a whole bunch of statements: read the temperature sensor, read a pressure sensor, read a flow sensor, just temperature, pressure, and flow, blah, blah, blah. Anyway, we've got several different several different sensors. We read them all, we do some manipulations. And then down here we have an exception handler for constraint error. And again, I told you that if you have a variable that's declared of one of these types where its range is restricted, and you violate the range bounds, you're going to get a constraint exception thrown by the ADA runtime system. Those constraint errors will be handled by exception handlers that are down here in the corresponding blocks, exception block. Okay? So you get an exception here, you'll handle constraint error there. The problem that we encounter here is that if you have a constraint error due to you're writing to a variable that read from the temperature sensor, you'll get a constraint error. Pressure sensor, similar, you'll get a constraint error. For all the variables that you have in there, you'll get a constraint error for each one of those different types of variables. It's difficult because you're handling constraint error, a variable of type constraint error. You just know, I've got a variable, it was a value was written to it that doesn't correspond to its predefined range. Well, was it my pressure variable, my temperature variable, my flow variable, some intermediate calculation? If you want to have more fine-grained notification about where that constraint error occurred, the association of your exception handlers with the block, if your block is big, doesn't give you enough information to tell where the error really is. So it becomes a challenge. One solution is this, where how about we just declare a bunch of blocks? Let's just chop this guy up into a bunch of different blocks. So we'll nest blocks and say, okay, we'll have a little block inside here where we read the temperature sensor and have a temperature sensor exception handler. And then we'll have another one for reading the pressure sensor, another one for the flow sensor, and so forth. Well, you can do that, but as the authors say, this is long-winded and tedious. You are really mixing up the flow of the regular code with the exception handling code, and as the authors argue in the text, that's pretty clunky. So, solution number 2, let's allow exceptions to be handled at the statement level. So suppose right here we've got a statement that reads the temperature sensor and puts that into a temperature variable, and then let's suppose we just, instead of having a block where we're defining the statements and then after that we've got exception handling code, let's just put the handler right there, right after the statement, or maybe make the handler just part of the statement of doing the executable that can lead to the exception. Well, the problem with this is that it really strongly binds exception handling code with normal execution code. You start to read code like this, and it's difficult to discern if everything's working right, what should this program do? And so it obfuscates the meaning of the program. Obfuscation, good word. Okay, so authors say the chill programming language does this. EH in here is exception handler. It intermingles the exception handler code with the normal operation, and it becomes less and less clear what the program is actually supposed to do. Okay, another solution here, which is what most programming languages take, is that you allow parameters to be passed with the exception. So instead of just passing a constraint error, maybe you can pass a constraint error, and this came from my temperature variable, or a constraint error, and this came from my pressure variable. So you associate some contextual information with the exception that you're raising. Okay, so Java, it's automatic. Ada doesn't allow you to really specify parameters that you pass automatically, but you do have this exception information function that you can call, and it will give you a little bit more detailed information about why the exception was raised. Okay, so next topic after discussing the idea of the domain of an exception handler and whether or not a block-oriented approach is sufficient, What we're going to say is that a block-oriented approach probably is the right thing to do, just as long as you're allowed to pass a little bit more information with the exception that you're trying to handle. Exception propagation. So this is the question of, well, okay, let's suppose I'm executing my program and I go through and I execute a set of statements inside a block and I encounter a situation where an exception is raised. What happens if that block doesn't define a handler for the code that for that particular exception that got raised? Okay? So the question then becomes, what's the right way to deal with this? Should we tell the compiler writers that they should insert code to generate an error every time that a block of code that can raise an exception doesn't have an associated handler for that exception? That's what it's saying. Should we regard this as a programming error that's reported at compile time? So the problem with that is that what happens if you divide by 0? The runtime system raises an exception. So if you're dividing by 0 and the runtime system raises an exception, inside the code that you're typing, there is no raise this exception statement. Your code does not explicitly raise the exception, but nevertheless you can have a synchronous exception that gets raised by the runtime system indirectly by things that you do. So there may be situations to where the compiler can't tell what types of exceptions are going to get raised by reading your code. And that's all a compiler can do is read your code. So not only that, it limits the context in which your exception can be handled. So an exception raised in a procedure can only be handled within the context of the procedure that it was called. Well, what happens if you want to propagate the exception that we'll talk about? So the way that Ada and Java and C++ handle this situation, when you don't have an associated exception handler in the block where the exception is raised, what that ends up doing is propagating the exception up the call chain. So I call a function, that calls another function, that calls another function, and let's suppose that third function in the chain raises an exception. And if there are no exception handlers in that function, then the exception gets raised in the context of the caller. And if there's no handler there, then it gets raised to that one's caller. And it goes back on up the chain. If the call chain ends up back at your operating system, which loaded the program and spun off the process, then your process dies. Okay? So that's called an unhandled exception, which is why when you dereference a null pointer, what Windows tells you is not you dereference the null pointer, it says unhandled exception. Because when what happens when you dereference the null pointer, an exception gets raised in your program. And you could put in an exception handler which would handle that exception, and you could keep that little box from popping up. But because of the fact that we typically don't put that in there, that exception gets propagated all the way to the operating system. The operating system says, and gets out its axe and chops your process. So what we have to do is figure out how to syntactically specify this exception propagation. Okay, there are two approaches that are employed in programming languages. One is called the resumption model. Another is called the termination model. Okay, in the resumption model, what happens is, so the question at hand, what we're trying to figure out is what happens after an exception gets handled. So let's suppose that we get an exception raised, it propagates up, we find the handler executes, and so you all seen Nemo, right? So you know right at the end when Nemo finds his dad and everything's happy, and then all the fish that are in the fish tank, what happens to them? You know, they get in the bags because they made the tank all green, and then they figure out how to get out the window and make it across, and they get down into the bay there, and now they're all bobbing in these bags, waiting to so they're all stuck in the bags, but now they're in the ocean, but in the bags. So in Blow's immortal words, now what? So okay, now you've handled your exception. Now what? Okay, so y'all are asleep today. I'll accept that. That's fine. So you've handled your exception. What do you do next? Should you return the control flow back to the point where the exception was raised? or should you skip it and go on? Both are valid approaches, and both have been employed. So let me make sure the answer. Okay, so what does C++ do? Does it resume, or does it skip and go on? How many of y'all have ever written a C++ program? How many of y'all have had a year of C++ programming? How many of y'all have not? All right. Yeah, you guys are excused. You guys know. I know. Your undergraduate curriculum did not serve you well. But at least, those were the grad students, by the way. Anyway, so those of you who've had a year of C++ programming ought to have learned exception handling. So, tell me, what does C++ do? Does it resume or terminate? It all terminates because whenever you get an exception, you just quit and stop programming. Yeah, pretty much that's how it works. All right. Java, anyone? Resumption, termination? Quit and go on? Why were you using Java in the first place? Okay, we'll figure this out. Some languages employ resumption, some languages employ termination, some languages give you the option. Okay, so we're going to discuss the resumption model. What the resumption model here is, let's suppose we've got three processes, P, Q, and R. Let's see if we can make these guys all appear at the same time here. Okay, so we've got P, Q, and R. So let's suppose that a procedure P, these aren't processes, these are procedures. Okay, so this is your code. I've got a procedure P. Let's suppose that P has a function call that invokes Q. And Q runs for a bit, and let's suppose that Q invokes R. And then R runs for a bit and says, I got a problem. And it raises an exception. That exception gets propagated up to R's caller, and R's caller is Q. Q has a handler for exception R, and we're calling that HR for handler for R. So the handler for R runs for a bit, and then figures out, oh, there's another problem, and the handler for R raises another exception, we'll call it Q. That gets propagated up to big Q's caller, which is P, and P defines a handler for exception Q. So now the question is, what should we do? So the handler for Q figures out, okay, I'm handling the exception. Let's suppose that he figures out the problem, solves the problem. Under the resumption model, what happens is control then returns back to the handler for R. So HQ resumes HR. Why does it resume HR? Because that's the code that was executing when the exception that the handler was handling, was raised. So HQ resumes HR, and HR then begins to run, finishes out handling exception little r, and then it resumes cap R, where cap R is the original code that we were running. So, doesn't that look good? Nice model. Anybody have any problems with that? Possibly. Tony might possibly have a problem with this. Okay. You'll tell me after I tell you. So the problem here is that you're going to encounter a situation, okay, why can you resume, why should HR resume cap R? Under the assumption that the situation which led to the exception being raised was fixed. Well, what happens if you're dividing by 0? How can you fix what the data value that your system produced was? Or how can you fix the instruction that divided by 0? Well, just rewrite the instruction. Do you like having your code modify itself? I don't like that. That just, I might give you a lab or a test question to do that, but don't do it in real life. So the problem here is the problem with this situation is that it's difficult to fix the cause of the exception. So there are certain circumstances where it makes sense, other circumstances where it doesn't. But this relies on the ability to kind of avoid the problem. So otherwise, you're going to end up with this infinite loop where R raises little r, you go up to the handler for R, you resume cap R executes that statement again, and it gets another exception, and you just sit here and buzz back and forth around in a circle because you're always raising the same exception over and over again. So, re-execution of the block is problematic. So this just summarizes what I just said. Termination model. Termination model, this is where you quit and go on. So here is some Ada code. So Ada does the termination model. So let's suppose here we've got this main block begin, and then the next sub block here begin. We'll read a temperature sensor that may result in an exception being raised. We have an exception handler for constraint error, and then we have some other code here that it gets executed when the block exits normally, and other handlers for other exceptions. Okay, so this is a diagram of what's going on with the termination model. So in the termination model, procedure P runs for a bit. It executes some code, gets to a point, calls procedure Q. This is just a regular procedure call. Q runs for a bit, and then it calls R. R runs for a bit, says, ouch, got an exception. Let me find a handler for that. I'll go propagate up to my caller. My caller, I'll see if it's got a handler. It happens to have a handler inside Q. We'll run the handler, and then quit and go on. Control does not return to R. Control does not go back up to the point where Q invoked R. It just goes from the handler block out to procedure P. Okay? So this is what you can see in this Ada code up here. So you've got some statements that may result in an exception being handled. So in the termination model, you've got, let's suppose an exception does get raised right here. You can handle that exception in the exception handler block that's associated with this sub block here. As soon as you're done, you don't go back up inside the block where the exception was raised. You just exit the block, and you go back down to this code that happens after that block. Okay? So likewise, if you have an exception that gets raised in this inside this sub block, and that exception gets raised, but there is no handler for it inside this nested exception block, the exception handling mechanism will check to here for a handler. If there is no handler, it'll jump down to the containing blocks exception block to see if there's a handler. So that's the propagation. Okay, hybrid model is where you provide some type of choice, where you allow the user or the programmer gets to say, I want you to resume or I want you to not resume. Okay, operating systems. So when you think about a program that runs, the program typically runs and interacts with an operating system. We've talked about this. We're building our operating system in this class slowly but surely. But nevertheless, Ada or Java, C, they all have to run in conjunction with an operating system. What happens if you have an exception that gets unhandled? There is no handler defined in your program. It gets propagated to the operating system. The operating system will whack your program and kill it. Okay? There are times where you can prevent that from happening. There are also within POSIX, which is the specification for Unix. POSIX is not an operating system, but a spec of interfaces that are required to be present in a POSIX-compliant operating system. So Linux and the various flavors of Unix are all quote-unquote POSIX-compliant, or can choose to be POSIX-compliant by supporting a set of program interfaces and libraries. So basically, when you see POSIX, think Linux or think Unix. Okay, so POSIX has the ability to allow programs to detect the presence of exceptions in the form of what are called signals. And you can define signal handlers. And POSIX supports the resumption model. So those of you who took my class last spring know all about signals and signal handling, or at least did at one point. But you can define signals and signal handlers where the operating system can send a signal to your program, and you can say, and you can react to the receipt of that signal. So for example, how when you end up dereferencing a null pointer, how this is handled in POSIX is that the operating system will detect, because it sees that you're accessing a memory region that you're not allowed to access. It'll detect that situation, and it will send a signal to your process. That signal corresponds to a segmentation fault. So it'll tell your program you've committed a segmentation fault. And then if your program handles the sig-seg signal, then it will run your signal handler. if your program has not installed a signal handler for the SIGSAG signal, then what will happen is your operating system will say, you've got an unhandled signal, and it will kill your process. So your program will die. You'll dump your core. Great. But if you do install a handler, then your handler will run. When your handler is finished, you go back to the location in your program that you were executing prior to the execution of that statement, which caused the signal to get raised. Okay. All right, we're going to skip a couple slides here. I'll let you read about exceptions and exception declaration. Basically, you can declare exceptions in Ada, and then you can raise the exceptions with the raise keyword here. So, and then you can query to see whether or not you've got different exceptions available. So, we need to talk about our C macros. Okay, well, just to give you a little bit more flavor here. Okay, so here's how you can declare some exceptions inside Ada. Each one you declare a variable. Its data type is exception. So you're saying sensor high, sensor low, sensor dead are all of type exception. Okay, inside the begin block, this is your guarded block in C++. That's where you'd put your try. After your exception is where you'd put your catch. But in here, this is where the statements which could cause exceptions to be raised. In particular, you could raise sensor low or sensor dead or sensor high or whatever. Okay. In your exception block, how you distinguish which handler goes with which exception is you use the when keyword. So when E : sensor high or sensor dead. So this is saying when I get an exception, I'm going to call that exception E. If that exception is either the sensor high or sensor dead exception, the handler for it follows as a double arrow. These guys are comments, but you'd replace that with actual code that handles that exception. When sensor dead, so if I get the sensor dead exception, then I do over here, I handle the sensor dead exception. Okay, there are also when others. So if I've got, all this is happening when I say, if anything else happens. So when E : others, this says if E is some exception that I haven't handled already within this block, handle it. So this is the default handler. And you can use some Ada internal methods to access information about that exception. Okay. The other deal is that, you can't read that. There we go. The other deal is that an exception raised in a handler can't be handled by the handler or that block. So if you have some exception code, if you have a handler that's handling an exception and it decides it needs to raise an exception, it doesn't loop back to the beginning of this exception handler block. That exception gets propagated up to the parent block of this block. Okay? So your handler code, you can't get yourself into an infinite loop. Say if you have while sensor dead or when sensor dead, you can't raise sensor dead and expect to go back up to that same handler. That does not get you stuck in an infinite loop. That sends the sensor dead up to your caller. Okay. So here's an example, and we'll use this in the context of explaining our C macros. Okay, so package temperature control, we're going to define the temperature subtype, define sensor dead and actuator dead exceptions. We'll say that this package has a method called set temperature. When you're declaring a package, this is kind of like defining, like what we had with our FIFO. This is kind of like a class in C++. This just defines the interface. Okay, package body temperature control, this is the implementation of the class. Okay, so we can define the set temperature method is, and we specify a begin block and some other stuff, and it might raise something. Okay, and that's the end of the procedure. So we're omitting a bunch of code here. Okay, but it's this is basically just the general structure of that Ada code. The begin block here is that's the beginning of this operation. Okay, so we can have that's the beginning of the package. Sorry. Yikes. There. So when we're initializing the package, we call the set temperature method that we're defining up here, and then we have an exception handler when actuator dead takes some exception or takes some reacts to something. Okay. Last wishes. So last wishes is we can raise an exception over here. What you can do with this is you can say You can have this allocate. It allocates a bunch of stuff. When you have some exception raised, you want to make sure to deallocate everything that you allocated and then re-raise the exception to your caller. So what this allows you to do is if you've allocated a bunch of stuff, you can clean it up without actually handling the exception. You can just re-raise it and propagate it up to your caller. Okay, so for C, what we're going to do is figure out what are the language facilities that we have for handling exceptions. Bullet point number 1, well, C doesn't have any exception handling facilities. What it has is a slick couple of functions that you probably haven't messed around with a whole lot called set jump and long jump. I really like these two functions. They're funky, they're weird, but they are very useful in certain contexts, and you can do a lot of fun, non-obvious things and impress people in job interviews if you know about set jump and long jump. Okay. Set jump is a function that you can call that takes your program status and saves it to a particular variable that you pass to set jump, and it will return a value 0. Long jump is a function that you call that will restore the state that you saved with a previous call to set jump, and it will cause control flow to go back to wherever set jump was called and start executing from that point forward. So it's kind of weird because set jump is a function that you call once, but it can return multiple times at different points of execution in your program with different values. The first time that you call it, it saves state. When you call long jump, it causes the system to restore the state that you saved from the set jump, and it'll cause set jump to return again, but this time with a different return value. It won't return 0 the second time. So when you call long jump, it makes set jump return again. So long jump makes you jump back to wherever set jump was called, and you return from set jump again, but you don't return with a value 0 this time. You return with a non-zero value. So you call set jump once to save the state. You call long jump to make set jump return, or to make set jump return a second time, but with a different value. Okay, so here's a structure of a program that you can use to do something like exception handling. Okay, so let's suppose we're going to define a type exception as a pointer to a char. Okay, then we're going to declare a variable of type exception called error, and we're going to set it equal to error in quotes. What does this do? So we're initializing the pointer variable error to point to a string constant. That string constant resides in global memory. It forms part of your program. This string gets compiled into your program. If you have 10 different string constants in your program, each of them will reside at a different location in your data section, or in your const section. Anyway, inside global memory, all of those string constants will reside at a different location. So if I have 10 different variables, all pointing to 10 different unique string constants, all of those pointer variables will have unique values. Remember that. That will be critical when you're doing this homework assignment I'm going to give you. Okay. Then you have this if statement here. If current exception equals casting as exception the return value of set jump save area. If that all equals 0, then do something else. Down here, do something else. Set jump, you pass the set jump a variable. This is where it's going to save the state the first time you call set jump. The second time set jump returns, that'll be the location where set jump returns or restores its state from. Okay? So save area is declared as a jump buff. That's defined in the header file or set jump and long jump or prototype. But anyway, so on this first invocation, what I'm doing is I'm calling set jump. I'm passing it save area to cause it to save the state of the system into the save area, and it will return 0, because when it saves state, it returns a value 0. I'm going to cache the value 0 to be of type exception, and I'm going to set current exception, which is a pointer variable, equal to the return value of set jump. So basically, I'm setting current exception equal to 0 on the first time through. Okay? So if current exception ends up being 0, then this is what we call a guarded region. So this is where I don't have any exceptions yet. This is how I start my guarded region. I call set jump and I save state. Now, inside here, I can execute a bunch of statements that maybe will raise exceptions. How do I raise an exception? I call long jump. I call long jump. I pass it the region that I use to save my state. And what do? I pass it error casted to an int. Error here was declared as a variable that points to some string constant. Okay? I'm pointing it as a string constant in order to get a globally unique identifier, a globally unique number. So I'm just using a nice funky trick here. I can declare multiple exceptions, each of them equal to different string constants. That way I can guarantee that each of the pointers take on a unique, different number. Okay? So what I'm going to do is I'm going to use that pointer value as an exception number. I'm associating the pointer number as the exception. So I'm going to cast error, or the pointer value that error points to that string constant, to be an integer, which doesn't do anything to the pointer. It just passes it as an integer because long jump expects an integer. So I'm passing this non-zero integer value to long jump. So what long jump does is it says, okay, go back up to set jump here. Restore the state that you saved inside this variable you passed to set jump, which is save area. And then cause set jump to return the value that you pass as the second parameter to long jump. So now set jump will return a second time. It will return the pointer value associated with error. So current exception will equal the value error instead of 0. So now this if statement will evaluate to a non-zero value. Control will go down, will not execute the guarded region again. It will go back down to this else block. So what happens in the else block? So the else block says, well, I only get here if I had an exception. So I'm going to query the current exception. If current exception equals error, I'm going to have a handler code for error. Otherwise, so if I have a different exception, if I say current exception equals error 2, I can have the handler for error 2. Error 17, handler for error 17, whatever. And then I have an else block down here at the end that says, well, I don't have a handler associated with this exception, so I'm going to raise it up to my caller. So I'm going to re-raise this exception in the surrounding domain. Something along those lines. So that would something along the lines of doing another long jump, yes.
Just to verify, so when long jump is called, it recalls the set jump?
So when long jump gets called, it doesn't recall a set jump.
Okay.
Set jump is this funky function. You call it once, and it can return multiple times. Okay, so it just makes it return. It doesn't actually call it. The difference is it doesn't push more stuff onto the stack and do a call instruction in assembly that goes, it just kind of does a jump, an absolute jump to the internals of set jump and causes set jump to do a ret.
Okay.
And that'll go back. So it causes control flow to return back as if you had just called set jump. It doesn't actually call it, but it just makes control flow to go back here as if you did. And so it will reevaluate the if statement. Yeah. Jonathan. Yeah, you can do multiple save areas and multiple set jumps. Okay, here's a bunch of C macros. Now the whole idea is make C look like Ada. So we're going to define several exceptions like begin, exception, end, raise, name, when, name, others, and so forth. Your homework assignment is to fill in the gaps. What are all these macros? This is a program that's out of the book, or this is a problem out of the book, and I will post this on Blackboard. But it's officially a homework assignment that is out of the book, but you're going to have to fill in the details for each of these guys. Okay, just realize you can abuse the preprocessor. This is a great way to do it. So we're going to make C look like Ada code with a preprocessor. And this is high time to not use the do while block inside your macros. What you're going to do is you're going to have snippets of C code associated with each one of these macros. This is what a program that you invoke with these macros would look like. So we can define, this would be a C program, but now it looks like Ada. So you invoke new exception and pass it sensor high to declare the sensor high exception, new exception, sensor low, sensor dead. You can have other declarations over here. So you have the begin block, raise, and then you may have some other statements over here that do some other operations, and then you have raise sensor high. So that will cause you to raise the sensor high exception, and you have this exception block, and you can down here say when sensor high, you've got the handler associated with sensor high, or when sensor low, after that you can have the handler for sensor low. you should be able to compile this with a C compiler and have it compile down to real C code. Okay? The -E on GCC is your friend. What that will do is it will emit the output of your preprocessor and save it. It'll print it up to the screen and you can save that. So as you're working on these exceptions, you're going to take your macro output and you're going to want to view it. If you just want to see what the preprocessor is doing and look at the C code equivalent of your macro code, then you can invoke -E on GCC and it'll tell you what your preprocessor output is. Okay, thank you.
Well,